Welcome to solverfy.
In this problem, we have a double slit experiment. So that consists of two slits with light shining through them, and they're separated by a distance d. And at some distance L away, there's a screen, and what you see in the double slit experiment is a fringe pattern due to the interference. So we have bright spots separated by dark spots. The bright spots are these circles here. And the equation governing the position of the bright spots, this is the mth bright spot, is given by d sine of theta m equals m times the wavelength lambda. And so what does that actually mean? You have to think about why this happens. So you get these bright spots because there's a path length difference between these two slits. And when that path length is exactly an integer multiple of the wavelength, then you get a bright spot because they constructively interfere. All right, so if you're when you're at the mth bright spot, then that means that the path length difference is exactly m lambdas. All right, so now what they tell us is that we're going to put a piece of mica here with an index of refraction n, and they tell us the index of refraction is 1.58. They also tell us the wavelength of the light coming through here in the vacuum is 550 nanometers. All right, so what happens, let's just look at what happens between these two slits with a piece of mica and forget about this fringe pattern for a second. So if we just zoom into that, the first slit, let's make it big, is going to go through some piece of mica with thickness S. And the second slit, for this distance S, there's no mica. All right, so inside this material, the wavelength is different. The wavelength in here, we write as lambda sub n, where lambda sub n equals lambda vacuum over the index of refraction. And the phase difference, or the phase, let's just say the phase for one of any given ray of light, is given as the wave number k times the distance traveled, which in this case is s. And the wave number is just 2 pi over the wavelength, and so that's going to be lambda sub n. So it's different for these two. And then times s. All right, so now the phase difference is just going to be the phase of this one minus the phase of the bottom one. So delta phi is now going to be 2 pi. So for the piece with the mica, it's 2 pi over lambda, and it's lambda over n, so the n is on top here, times s, and then minus the phase where there's no piece of mica, so that's just 2 pi over lambda, n equals 1, times s. This is equal to 2 pi s over lambda times n minus 1. So that's the phase difference. And they're telling us that that is equal to the 7th fringe. Up here, this means that the 7th fringe just got moved down, essentially. So if it's the 7th fringe, then the path length difference is n times lambda. That means delta phi, which is equal to 2 pi s over lambda times n minus 1, is equal to a phase of 7 wavelengths. So that's going to be 2 pi for lambda, and then the distance is 7 wavelengths, so that's 7 lambda. All right, so here we have the lambdas cancel. There's a 2 pi on both sides. So now we have that s times n minus 1 over lambda equals 7. Solving for s, we have that s equals 7 lambda over n minus 1, and plugging in the numbers, which were that n is 1.58 and lambda is 550 nanometers, we find that the thickness s is 6.6 micrometers.